and we'll record on this computer. So welcome back to CE 529. That's a good point. Thank you. Oh, I am unmuted. So what's mute is the phone. Oh. So this is unmuted. Thank you for the reminder anyway, because I think it didn't come through today, but I'm sure there will be days that I'll be recording muted like last time. So thank you for the reminder. So we're going to get started with like real quick discussion of the Muddiest point survey. I think a lot of you did take that quick survey, so I appreciate that. And I want to go back to the results there. So this is your Muddiest point survey. So it looks like, most of you got the hang of, how the class is going to work and all of that. That's great. Role of traffic volumes, because we did have this big discussion about how the traffic counts could be used. You need the origin destination flows, but then when they come out of the simulation package, they come out as traffic count on individual links. So and then you can use those individual link counts from the real world for validation purposes. So that was so it looks like most of you got that part as well. So data requirements for the simulation model, and I think there are some confusion, and that's basically what the homework is for. And hopefully you got a chance to do a little bit more digging deep and research into it. But the idea is that you want to create the most realistic replica of your transportation model. And for us to do that, and obviously as you sort of get into more advanced models, you get to a part where you need to make sure that your geometry is correct. You want to make sure that you have some information on the driver behavior. In the past, in the simulation studies, we've had to collect the kind of gaps drivers would accept versus the kind of gaps the drivers may reject. So broadly classifying that would be the behavioral data. So as you get into more micro level modeling, microscopic modeling, you need more and more data and behavioral data, how pedestrians and bicyclists might interact with the cars and the trucks, how many car and trucks are out there. That could be another sort of wrinkle into the traffic volume data. So the way I want you to think about the data is, what is the purpose of your model? If you're doing a micro level modeling, you need a lot of data. And then you could classify that data into different groups. And the first group could be simply traffic volumes. But within traffic volumes now, you could get peak hour data, you could get the truck percentages, you could get other things like bicycle data, pedestrian data, things of that nature. And then you could get like, what's the breakdown of that data? Is the data coming into chunks? Like, is the traffic volume, basically looking at the peak hour factor, right? So those are the things that become important within traffic volume. And you'll have the geometric design data, basically the context and the environmental data. How wide are the lanes? Are there bus lanes? Are there bike lanes? What type of bike lanes they are? Class 1, class 2, class 3, class 4. What is going on? Is it a sharo? And what's going to be the, and then, so this is all the data from the environment, like the geometric design of the network. Signal, if there is signal, then you'll need the signal timing data. If there is stop sign, you'll need some, where the stop signs are located, where the stop bar is located. And then the next set could be the behavior data, the user data, right? How the users are interacting with the system. So you want to make sure that you're replicating that correctly. So maybe, you might be looking at the environmental data, you might be looking at a stop sign, where that stop sign is located. But when you go out in the field, and depending upon how large your network is, right? If your network is too large, sometimes these types of details are not practical to collect all the time. But if you're modeling like one intersection, then it might become important for you to look at first where the bar is located, right? On the stop sign, where the stop bar is located. But then you might want to assess the behavior of the people there. Are they stopping at the stop bar, or are they stopping maybe 10, 20, 15 feet ahead of the stop bar? And why is that happening, right? Is that happening because they actually cannot see who is coming from the right side or left side or whatever? The right side coming from traffic coming from the left might be particularly hard to see. And I'll give you a quick example of that. If you are coming down on California Boulevard, so let me quickly show you the map there. Let me quickly zoom into the map here so if you come out Cal Poly, If you're coming out of Taft Street here, I don't know if I can get the satellite thing on. Yeah. So if you look at this data coming out of Taft Street, look where the stop bar is located. Right? You could probably spot that. Not able to annotate this, right? So let's look at where the stop bar is located. Stop bar is located right here, right? But if you actually go out and observe the behavior of the people there, if you stop here, it's very, very hard for you to see what's happening, what traffic is coming on from your left, right? So almost certainly you have to actually make the stop over here. And I have a little story to tell, and I was teaching a class back then. I don't know if any of you were in that class, but maybe 3 years ago, or maybe 4 years ago now, almost 3.5 years ago, I actually was cited by a police officer for not stopping on that stop sign. And we used to live in a Atascadero back then, where this was sort of my dad. We were about to move to San Luis, by the way. So maybe within 3 weeks of that location, or three weeks of the relocation, I was stopped and I got a ticket here because the cop said that I actually was stopping here and not here. Right? So basically what happened, so the ticket was fine, but obviously I had to contest it because there is a problem with this location and you try to assess the behavior, right? So actually I fought that ticket, but the cop didn't show up. Otherwise I would have set a precedent. Nobody could get a ticket for not stopping on the stop sign, but that unfortunately didn't happen. I was very well prepared with all the videos. And when I was actually taking the video, I had a cop come out on this intersection, and basically that cop basically stopped here because they couldn't see what's going on. And I had that video on me as evidence, but I didn't get a chance to present that. And that's okay, but I actually took all my evidence, and I was teaching, I think 222 or C322, one of those classes. And I said, I've got a captive audience. I couldn't present it to a judge, so I'm just going to present it here. And ever since then, I've been using that example, regardless of what class I'm teaching, whether it's safety, simulation, doesn't matter. But the idea for simulation that's important here is that in simulation, what you might want to do is you might want to basically place that stop bar here. If most people are actually stopping over here, so this is where you want to place the stop bar, because that will dictate how the vehicles merge on the street. And again, this may not be possible all the time, right? If you have a very large network, like we've been modeling networks of City of Atlanta, or we've done some modeling for the whole downtown San Jose network, then it's very hard to kind of capture all of these. And if you're doing that level of analysis, maybe you don't need all of the details of all the individual intersections, because you don't need that many details. But if I was just analyzing this situation or what solutions might work here, I would have to maybe account for that behavior. Okay, so it's very context specific, a problem specific issue. Okay, so we can close this out. So that's kind of like, when you're thinking about the data, the context is important, and then big picture, big categories of data. And then within those big categories, you have, so big categories would be traffic volume, environmental context, and user behavior data. So those sort of become your three big attributes of data. And then within those, you can define subcategories of the type of data that you might want to put. Okay. And then strengths and pitfalls of the modeling and simulation approach. So if you're wondering about, and again, as you can see, if you're modeling a big network, you might be missing out on certain details. But if you're modeling a small network, then you will need all those details. And if without those, and those details can be very time consuming to collect, very time consuming to model appropriately. But once you do that, the model can be very robust for you to test out different scenarios. So that's basically the big picture strength, is that you could do a lot of good things that you otherwise could not do with the real system. The big downside is that you need a lot of good data and a lot of time and training to be able to do all of that. But that's basically what this class is about. Okay. And then different categories of models. And again, we will sort of play with this information, this question throughout the class a little bit. But these are different categorizations, static versus dynamic. And when I say static simulation, I'm talking about things like, what we did in the class, the Monte Carlo simulation approach, where we were sort of in our lab 0, where we were trying to simulate the dart throwing process using Excel. So time plays no role in that. And that's basically becomes your static modeling or static simulation. But the dynamic simulation always involves time. Now, there is a little wrinkle here that I want you to understand is when I say static, and we're going to get to that a little bit today as well, the idea is that we'll mention something called a static traffic assignment. Okay? And static traffic assignment means what we use in the modeling process, the link performance functions, they don't change over time. That's what static traffic assignment means. So in simulation models that you're going to develop for the most part in the class and even in the real world, most of those simulation models could in fact be static. Sometimes they refer to it static simulation models. But that's not quite accurate. That what you're actually meaning there is that they're static assignment traffic simulation model. That the traffic assignment approach that we are taking is static, means that our link performance function does not change over time. Okay? So it doesn't mean that the model is static. Obviously, the traffic volume and everything is going to change with time. So the model itself is dynamic, but the traffic assignment that you may be using most of the time would in fact be static. So don't get confused between those two things. I don't have better terminology to explain that, but it's just that static traffic assignment models is what we are mentioning when I say, static simulation model or static traffic simulation model. Obviously, the model itself is dynamic because all the traffic flow will change based on time. It's just that the links, the link performance function, how the link performs as you add more volume to it, a lot of time that would not change based on time. And we're going to talk about the dynamic traffic simulation models a bit also in the class, just so you are familiar with the concept, that if you ever have to apply them, you have some concept in your head that these kind of things might exist, but we're not actually going to go deep into actually modeling that type of system. Okay, and then discrete versus continuous. Again, discrete is all these models are discrete models. Continuous model only come into play when you're treating the whole movement of traffic as a flow, a fluid flow. Okay, so most of the models that we're going to see in this class, in the simulation sense, all the models that we're going to develop in the lab, they're all going to be discrete models because we are interested in the individual movement of vehicle flow or traffic flow. And then micro versus macro. Micro is the smallest possible scale individual vehicular interaction. And then macro is again big picture. Macro type of models are what you develop in CE 523. Okay, so those would be the models that you do for travel demand forecasting. When you have 5, 10, 20 years time horizon, and you're just basically trying to figure out how much flow can I expect on average on a certain link. I'm not really interested in individual vehicle flow or individual sort of movement of individual vehicles and pedestrians and bicyclists. Maybe I just want to know what's the total number of bicyclists. And in that case, I'm mostly looking at macro level models. So I hope those things will clarify a little bit. Some of this was repetition from last time just based on this survey, but I thought I would clarify. Yes, please.
When you say the simulation in the video we watched, is that micro or macro?
In the Cal Poly, so the question is, the simulation video that we watched for Cal Poly campus last week, was that micro or macro? So I would classify that as micro level model, even though it was a big location, but we did model the interaction of individual vehicles and individual road users. So all of these, so VSIM, when we use VSIM, that's a microscopic simulation model. So we're always doing micro level modeling. Within that micro level modeling, if our study area is large, we're bound to miss some details, right? And that's okay. That's perfectly acceptable, depending upon what we are trying to do. But sometimes we are interested in just one intersection, one location. That is also a micro level model because we are modeling individual behavior. But then in that case, you might want to be very, very accurate because you're focusing on just one location and you can afford to be more accurate by gathering more and more information.
But the same is always micro.
VSIM models are always micro level models. Yeah. And then there are other tools like if you're like, what is a macro level model? Or so a macro level model would be something that you develop using Transcat or Cube, right? So those are your sort of macro level long-term planning models. All right. So with that, are there any other questions? If there are no questions, what I'll do is I will.
So is macro more like just monitoring like flows and each
Aggregate flows and yeah. So the question is, what's a macro level model or macro flow? So macro would be, and we're going to see some of that in this class also a little bit towards the end, but not in the simulation sense, but in the modeling sense. So the idea that you could do, if you recall, flow is equal to speed time density. So that's basically your definition of the uninterrupted flow, defining relationship of the uninterrupted flow. You say the volume or the flow rate of traffic, vehicles per hour, is equal to the aggregate space mean speed of the traffic times the density of traffic on the traffic lanes. So when you apply that relationship, that's a macro level relationship. Because that's not bothered by what's happening, how individual vehicles are interacting. But what we're going to show you in this class a little bit later, I think around week 4 or 5, is that actually the assumptions that you make, how vehicles interact with each other, that has implications for what assumptions you're making for the macro level flows. Okay? So we are going to get to that a little bit in week 4. So we're going to show you some sort of convergence between the micro level interaction assumptions and macro level flow relationships that it results in. But macro level is when you're not concerned about individual vehicle flow all that much. You're modeling it as a whole. Okay, so what I want to do next is I'm going to get started on this traffic assignment. Okay? And this is basically, we're looking at user equilibrium for traffic assignment. And I used to teach this class about 3 years ago, and then we had Professor Molan, who was here for a couple of years. So I shared all my materials with him, and he updated that material. So I want to make sure that I acknowledge his contributions to this as well. So he's one of my collaborators. He's now a professor at Ole Miss. So he sort of refined the notes that I had provided him, and we worked together on building this module. So first, let's try to define what is traffic assignment. So traffic assignment is determining which routes will be used by different origin destination pairs. And then based on that, figuring out how much traffic could be expected on each route. Now we do traffic assignment in macro level modeling as well. So if you think about Transcat, what we do in Transcat, how many of you have taken CE 523 travel demand modeling class? So just 2 of you? Okay, 3. All right. So yeah, so then you remember, so only 3 of the 13 or 14 people we have in the class. So I'll kind of go back one step further from CE 321, right? In CE 321, we think about how traffic will go into different routes. Okay, and that's basically what simulation is about. When you model any network in vSim, you define routes, and how much traffic will go into these routes is a traffic assignment question. Okay, now you make certain assumptions that that much traffic will go in that route, and then you put that traffic in the route, and then you count, and then that count can become sort of your validation measure, because you can compare the count from the simulation with the real world. Right? So how much traffic will go into each route? It's a very critical question for us to think about in simulation. And there are sort of mathematical ways of doing that. So we're going to get to that a little bit. So traffic assignment is part of the travel forecasting model. Okay? And travel forecasting models is what you learned in your CE 523 class. We talk a little bit about that in 321 as well. So when we are doing long-range forecasting, we evaluate the impact of future changes in demographics, land use, or transportation facilities on the performance of a region's transportation system. So the network that I'm going to show you, I'm showing you here on the slide, is actually very large network. And this kind of a large network, you're never going to do micro level modeling within this network. Right? It's going to be very cumbersome for you to do micro level modeling. And it won't be even that useful for you to do micro level modeling at this range. It's such a large network. But that level of network, what you might be interested in is what's the overall travel speeds on these networks. So you could see some links are red. So that means there's more congestion there. You're not interested. So this is sort of, these green and red lines are potentially showing you, or different colored lines are potentially showing you the aggregate performance of those links. Right? So you could look at that. So this is, and then we can do that at the macro scale as well. So we can do in 20 years time, this is what the network is going to look like. This is going to be the demand on these different links. And we're doing traffic assignment model to figure how much flow is going to go into individual. So if you remember traffic assignment from 3HC 321 or travel demand modeling discussion from 3HC 321, traffic assignment was the last step of the travel demand forecasting model. It was the last step. You remember the 4-step travel demand model? What are the steps of the 4-step travel demand model? Where do we start? Trip generation, yeah. Distribution, very good. And then mode choice, and then trip assignment, right? So that's exactly right. So trip assignment was the key step, the key final step. And why is that the key final step? Because this is something that you can validate your model with, right? Because it's going to be hard for you to measure how many people are going from one origin to one destination, but it's very easy to count the traffic on the network location, right? So that's why, so this was sort of the last step of the travel demand forecasting process, and we want to know how much traffic is going to use each link. So I'm glad that you guys remember that 4-step travel model, because we are going to recall some discussion from 321 here to be able to do this. So when you're trying to do traffic assignments, here are some of the data that you require when you're doing traffic assignments. So this is sort of network location, and you have origin on this side. You have origin here, right? Here is the origin. And then here you have the destination. Okay? And then there are 3 potential routes that can take you from that origin to destination. There are 3 potential routes that can take you there. So what you need is number of total trips between the zone pairs. You need available highway and transit routes between the zone. You travel time for each zone, and then decision rule to determine the route selection. Right? So anytime there are more than one route, you need some sort of decision rule to figure out what that distribution flow would look like. But there is a wrinkle to this, and that wrinkle is, and this is a very important concept in transportation planning and travel demand modeling and simulation modeling as well, is that when I say the third item, the travel time on each route, the travel time, generally speaking, is not a constant. Especially for the automobile mode, travel time is highly dependent on how many people decide to use that. Right? Because even if the route might be, one route might be the shortest travel time route, when nobody is using any of the routes, but as people start to use the route, that route could become congested, and now some other route might become more competitive, right? So in your model, this is something that needs to be accounted for. Anytime there are multiple routes, you need to think about what that travel time looks like for you. Yeah. So let's think about, so these are the data required for you to okay. And then once you figure out how much cars are going to go there, then you can basically, the output of that could be used to estimate the zone to zone travel times, link flows and heavily congested links, the routes used between OD pairs, and then you could use also to get the turning movement count on individual nodes or the intersections on these routes. Yes.
So what is your opinion on like the fact that those three routes will always be in equilibrium?
Yeah, so that's kind of what we are going to discuss today. So the question is, are those routes are going to be on equilibrium? Yes, in a steady state, that's kind of what has to happen, right? Because if you know your travel time, and generally speaking, people will try to minimize their overall travel time, then there would be always the same number in equilibrium scenario. That has to happen. So if you're, and then, so that's basically what the static traffic assignment principles are about, is to establish equilibrium of travel time between different routes that we are using. Because the idea is that anytime one of those routes has a shorter travel time, people will go and switch to that route, right? And then that route will become congested, and then basically people will keep switching until an equilibrium is established. So that's basically the idea of the static traffic assignment, and that's kind of what I'm trying to get at. And that's your sort of your user equilibrium principle. The route choice behavior is often considered based on Waterup's principle. The first principle is user equilibrium. Second principle is system optimal. And then we're not going to talk too much about system optimal in this class. We do talk about this in transportation economics and analysis class, where we talk about tolling and how we can use the tolls to then sort of establish system optimal routes. So I'm not going to get the second principle into too much, because that's your CE 528 stuff. But the first principle, user equilibrium, is very useful when you're doing simulation modeling, because that's the whole idea, is that you let people choose their route, and people will choose their route by trying to minimize their individual travel time. And that has some interesting implications for how we manage congestion and so on. So two important assumptions of user equilibrium principles. They are, drivers will choose a route based on travel time, so based on trying to minimize their individual travel time. That's one assumption. The other assumption is that drivers know the travel time that would be encountered on all available routes. So I want to just pause here for a second. I want you to think about, what do you think of these assumptions? Are they very strong assumptions? Are they reasonable? What do you think about this? Are these reasonable? Yes, please.
I always feel like iPhones make these assumptions. We're kind of assuming the iPhone does all this for us.
Yeah. So basically, the response is that they are reasonable assumption, especially given the penetration now that we have with all these maps and tools, online maps and so forth. You can always look up where the travel time is minimum, and you can, people do that with apps like Waze and stuff like that. So very, very accurate crowdsourced information can be provided about where the congestions are. Travel times could be predicted. Obviously, these things are not foolproof, but for the most part, for most networks, you can make an assumption that yes, people know what their travel times are, and then they will choose the route that has the least amount of travel time. Yes.
Google Maps is using more like their recommended route is
Yes.
With this assumption, would that shape this assumption?
Yeah, I think that might. So the question is, now that Google Map also starts recommending travel time that have lower greenhouse emissions, is that going to change a whole lot of things there. Now, this is an interesting one because, yeah, so that might change things around, especially when you're talking about sort of non-commuter travel. For commuter travel, I think that perfect information also comes from experience, right? So if you're using that route based on your experiences, then those routes might be based on your experience, and you might not, as a commuter, you might not even be looking at Google Maps at all, right? So for commuter traffic, that probably doesn't change too much. I think if you're analyzing a location where you're especially concerned about holiday traffic and stuff like that, that might come into play a little bit, and you might want to rethink how this plays into it. But that's a good question as to. But I think even before we had Google Maps, we always made these assumptions. So the analysis that we're demonstrating here is not something that we've done like last 10 years. We've been making these assumptions for a long time, because a lot of time we're concerned about the commuter traffic, and commuter traffic is based on the experiences that the travelers had. So those are still reasonable assumptions. Yes.
Like I think these are like good assumptions that we make. Like this like describes like my personal behavior, but I'd like to think that like maybe for each person who's like looking on Google Maps all the time and like has all these other routes in their head, there's probably other people who just take the same route every day no matter what. Like they only know when we get there. Like
yeah, and then that's basically right. So as I said, like so these are sort of, you could say that these are reasonable assumptions, not necessarily foolproof assumptions. They don't apply 100% of the time. And there might be contexts like holidays, like maybe days then when you have like a major collision or something, these assumptions would get violated, because if you have people like that you're mentioning that will take the same route no matter what, never look at the map, then they will get stuck on that route, and then you will end up with routes that have significantly higher travel time than the others, right? So yeah, so there would be days or times where these assumptions would get violated, and you have to be sort of aware of those contexts. So for example, if you're just trying to do like a peak hour modeling for a location, then you will just think of these assumptions as sort of reasonable and go along with those. But let's say your study objective is you want to look at what should you do if there is a collision on Cuesta grade somewhere. And I don't think there is much you can do, because there is no other real route to cross to North County. So maybe that's a bad example. But think about if there is a big collision on Highway 46 going east, right, towards Bakersfield or wherever. So maybe then you have to think about what maybe Route 166 might be a better route, right? So again, so you have to think about like, what is your modeling objective here? If your modeling objective is model the normal peak hour traffic and then introduce some scenarios there within like, some conversions of some streets to one way or whatever it is, then that's one thing. But if you're sort of trying to model what would happen, what should we consider the alternative routes to be, then maybe these are not good assumptions. So then you might want to think about what is that? What are my assumptions at that point? What percentage of drivers would consult the travel map? Things like that. Yes.
what like level of confidence would you put in these assumptions? Like would you tell somebody like, oh, like, this travel time is going to be accurate 90% of the time?
Yeah, so this is something that you kind of get from the model. You basically do that. So all the time when we're talking about standard errors, those standard errors come from, so the question is, how confident should we be in these assumptions? That depends on, how many runs have you done of the network? So if you just do one run or two runs or fewer runs, then you're probably not going to be as confident. But if you do multiple runs and you get similar results, then you can, based on that, based on your sample size of runs, you can estimate that, I can be reasonably confident that, and you can basically within those runs, you will have different seat numbers, some minor fluctuations in demand. And then based on that, you can actually estimate the standard error of like, if you do 10 runs or 20 runs or 30 runs, based on that, you can estimate a standard error on the actual travel times that you're getting. So you can then report back those that, so this is my 95% confidence interval based on how many runs did you do. So more runs will give you like a shorter confidence interval band, and then you can go with those. So great questions. So concept of equilibrium is meaningful because we can assume that most travelers have discovered the shorter route. And then there are ITS systems and maps and all of that that can make travelers much more aware of the network conditions than that were typical in the past. So there are tools out there and people will have reasonable assumptions. So I think our reasonable information to make decisions. So we can sort of take these assumptions and use that in our model. Basically, that's the bottom line. So this is an example that we used to do in CE 321. And I want to quickly go, how many of you think that you can solve this problem? Recall that from 22. So we're talking about performance function here, link performance function. Right? So, and we are going to try to establish equilibrium. It's in thousands of vehicles per hour. Okay, so I'm going to try to solve this problem very, very quickly because I'm hoping that at least some of you remember this idea. But my main goal is not to solve this problem because we've solved this problem in 321. What I want to do is I want to extend this problem to multiple routes now. To get a sense of equilibrium, what happens when you have not just 2 routes, but 3, 4, and 5, and 6 routes? What happens in that scenario? Okay. So what I'll do is I will stop sharing here. Sharing completely, but okay, maybe I'll stop sharing and then film this. And share my screen. Okay, so I'll have to stop share, but I'll write down the problem here. Okay. So okay, this is what's going on right now. So you have, there is an origin, and then there is a destination. And the total demand from origin to destination is 3,800 vehicles per hour. Okay. And then right now there are 2 routes that take you from origin to destination. And those 2 routes have link performance functions. Those 2 routes have link performance function that look like this. Four plus 3x1 and 2.2 plus 6x2. And then these basically define your travel time, each of the routes. Okay. These define the travel time on each of the routes. So what basically this tells you is that if there were nobody using this route and you were the first driver, then to go from origin to destination, it will take you 4 minutes if you took route 1, because x1 would be 0 in that case, where x1 and x2 are travel demand flows in thousands of vehicles per hour, VPH. VPH is vehicles per hour. The total flow is 3,800 VPH. That is basically, I'm going to just call them 3.8 units or 3.8 thousands of vehicles per hour. So I'm going to define my units based on that. Where X1 and X2 are travel demand flows in thousands of vehicles per hour. And then so what has to happen if these are the two flows, 3x1 and 2.2 plus 6x2. So these are what happens to travel time as you add more vehicles to the network. Right? So if you add more x2, the travel time would increase, and this function defines how that will increase. So now let me ask you this: if you're the first driver, which route would you choose? Route 2, right? Because it only takes 2.2 units of time, whatever that might be, minutes, let's call it minutes, to go from your origin to destination. So we'll choose that. And people will keep taking that route until what happens? What has to happen? The route 1 becomes competitive. What has to happen for that? Yes.
The travel time on route 2 has to get to 4 minutes.
Yeah. So when the travel time on route 2 becomes 4 minutes, that's when route 2 becomes competitive. And that's a very important threshold for you to find, because until that happens, nobody will take route 2. Based on our user equilibrium principle, everybody's trying to minimize their travel time. So this threshold for route 1 to become competitive can be determined as when 2.2 plus 6x2 becomes equal to 4. And I can figure out x2 is equal to 4 minus 2.2 becomes 1.8. So x2 equals 1.8. Oh no, 6x2 becomes 1.8. So x2 becomes 0.3. So anytime the flow is below 0.3, oh no, yeah, so that's right. So anytime flow rate is below 0.3 units, what will be your answer? So anytime the answer, like if somebody asked you, if the total demand flow, instead of being 3,800 that I defined at the beginning of the problem, the total demand between origin and destination was only 200 vehicles per hour. What would your answer be for the user equilibrium flows? If the total demand were 200 VPH, what would happen? What would your answer be for user equilibrium flows on each of the routes? Everyone takes route 2, your answer would be 200 vehicles per hour to route 2, 0 vehicles per hour on route 1. Because route 1 hasn't yet become competitive, and it only becomes competitive at 0.3 units. But when you exceed 0.3, then it's very easy to solve, right? Then what would be your answer? How would you solve it? If anytime your total demand, let's say total demand is 3,800 VPH, as we said. But if total demand is 3,800 vehicles per hour, what happens? You set the equilibrium equations up, right? And equilibrium means travel time on both routes has to be equal, because unless that happens, there is no equilibrium. People will keep switching their routes to minimize their travel time even further. So you can set up two equations, because you have two unknowns, x1 and x2. You need two equations because there are two unknowns. So two equations would be, first will be the travel time on both routes is equal. So I'll say 2.2 plus 6x2, 4 plus 3x1. 4 plus 3x1 has to be equal to 2.2 plus 6x2. What's your other equation? Yes. Yes, that's exactly right, because that's your conservation of flow. So this is what we call the conservation of flow. That means no vehicles are getting lost. And if the total demand is 3,800, they're both, that is being divided between the two routes. Okay, so yes.
Is 3.8 given?
Yeah, so 3,800 vehicles per hour, right? If the total demand was 3,800 vehicles per hour, you can translate that because the units are in thousands of vehicles per hour, right? So that's where I got the 3.8. So it's very important for you to pay attention to the units. A great question about 3.8. How do we go from 3,800 vehicles per hour to 3.8? Because we're defining X1 and X2 are travel demand in thousands of vehicles per hour. And so you have to look at the demand unit carefully. Now, the question is, now you got one more route. Let me go back and share screen. Now let's see. You got this problem now. As travel increases in the corridor, a new route is tried. A county road that used to have a gravel surface has recently been paved with asphalt. Now the free flow travel time through the corridor is 5.8 minutes. Okay, so there is a third route that they introduced. The free flow travel time through that route is 5.8 minutes. The average travel time increases on this route by 1 minute for every 1,700 vehicles per hour increase in hourly volume. Okay, so the next question for you is, based on this discussion, or based on this statement, just this statement right here, based on this statement, based on basically those two things, 5.8 minute travel time, and then this 1 minute increase for every 1,700 vehicles increase in hourly volume. Can you write the link performance function? So let's go ahead and take a minute to write the link performance function here. What would be the link performance function for what is essentially a third route that I'm introducing here? So I'm introducing a third route between origin and destination. And that third route, I want to write the link performance function for that. I know the free flow travel time. Now think about what is free flow travel time. Free flow means there's nobody else on the road. You're not affected by anybody else on the road. That's what we call the free flow travel time. And that's 5.8 minutes. And then the travel time increases by 1 minute for every 1,700 vehicle increase in hourly volume. So can you, based on this, write what would be the equation? What will be the link performance function like it was? It used to be for the first route, it used to be 4 plus 3x1. Can you come up with a similar equation? Yes, Tina. Yeah, that's right. So the response that I got from Dana is it's 5.8. That's your free flow travel time plus 1.7 because the units are in thousands of vehicles per hour. 1.7 times x3. So your link performance function here becomes T3 equal to 5.8, which is the free flow travel time plus 1.7. That makes sense for everybody? Yes.
Doesn't need to be 1 over 1 plus 1.7 because you need 1,700 vehicles to add it. So like when you do that multiplication.
Yeah, so no. So travel time increases by 1 minute, right?
Yeah.
So if you, oh, that's right. I should probably say, so that's a great point. And that's why I see, it's a great point. So I should probably rephrase this question here instead of changing my equation. So that's a good point. So I should be thinking about this. Yes, where you look at this, I will. So I should say by 1.7 minutes for every 1,000 vehicles. Is that corrected? Sorry. So yeah, this is a great question. If you didn't catch me like this, I would have said that I did it on purpose to make sure that you all were paying attention. And now I've recorded that I made a big mistake, but that's okay. So yeah, this is a great point. So when you're thinking about this equation, this is the right way to think about it. The travel time increases by 1.7 minutes for every 1,000 vehicles per hour increase. So that will set up the equation that Dana was talking about. I'll go ahead and share my screen back. So if you look at this, so that will give you 5.8, T3 will be equal to 5.8 plus 1.7 x3. Okay, so I'm going to stop here. And in the next class, what we'll do is we'll pick this discussion up and see how do we solve a 3-route problem. And then we'll try to generalize it to 4, 5, 6 route solve. Okay, all right. So I'll see you in the lab today. And then we'll go from there. So be on time because I have another guest speaker who's going to talk about one of the job opportunities she has. So I hope you all can make it. And then we'll obviously have our lab discussion. Thank you.